since this is quite a bit, there's a lot of calculations that come into thermochemistry and calorimetry. So that's the topic of our workshop today. So this is how we're going to break it up basically. I am going to go over the basics, like what the equation of thermochemistry is. We'll do a practice problem together. You guys will do the following ones on your own. Then we'll go to calorimetry, more practice problems, and then I'm going to supply you guys with some challenge problems to do. Okay. So let's go to the first part. And it is your thermochemistry equation. So the equation, this equation Q equals to mc delta T, is you're calculating the energy that is released or absorbed when an object experiences a change in temperature, which is the delta T. So M is your mass in grams, unless stated otherwise. C, which is your specific heat capacity of the object, is in joules over grams times degrees Celsius. And then your delta T is in degrees Celsius. So T final minus T initial. The energy of this equation that you're calculating, it can be also referred to as Q absorbed and heat released. So the negative just means that released energy is exothermic, absorbed is endothermic.
So you mean if the equation, say, if its releases energy, it releases heat.
Yes.
So it is negative.
Yes. So
the delta, like delta H, is negative.
Yes, you can say delta H or delta E even. So what this is just drawing a relationship between the energy that is released and absorbed.
But so, we can say the opposite, that like Q release equal minus Q absorb.
Yeah.
Right? Because this is like algebra.
This depends on how it's set up. So this is just the basics of the relationship of it.
Okay.
Yeah. So we'll do the practice problem. So for the first problem 1, the question is asking you how much heat is required to warm 1.50 kilograms of water. So this is your mass. But remember, your mass is in grams, so you are going to convert it. From 10 degrees Celsius, T initial, I like to label whenever I'm going through the practice problem, to 90 degrees Celsius, which is your final temperature. Given that the specific heat of water is 4.184 grams, so this is your C. Let's write down the equation, Q. Okay, so we're going to do Q equals to M times C times delta T. So what we'll first do is we will convert your 1.50 kilograms to grams. So in 1 kilogram, there are 1,000 grams. So then you just end up with 1,500 grams of H2O. Then I would do my delta T calculation, which is the T final minus T initial. So it is 90.90 degrees minus 10 degrees Celsius and that's equal to 80 degrees Celsius. With all the information now, we can just plug it into the equation and you guys can solve it. So Q equals to 4.184 joules per grams degrees Celsius. What you'll see is your units are being canceled. I always remind students to make sure that your units are being canceled. You want to make sure that you're only left with the unit that is desired for your answer. Degrees Celsius. So here I'll just cross out the units that are being canceled out. Your grams are canceled out on top. And you're left with only joules. So let's plug this into the calculator.
502,080 joule.
Yeah, so 502080. That's a big number. We only want to have
3 sig figs.
3 sig figs. You're going to disregard the temperature in this case. It's only 1. So 3 sig figs will be our
5.02 by 10 to the 5th joule.
Yes. 5th joules, and that's your answer.
But it is negative or positive?
So in this case, it is a positive. We're not doing any relation to heat being released or absorbed. But, okay, so we're not doing that relationship yet, but if you're looking at this, how much heat is required to warm? If you're putting heat into a system, so you're heating it up inside, heat is going into it and not out of it. So it's endothermic, so it would be positive, right? Heat is absorbed. So this is saying that you're starting with cold water, and if you boil it, basically. So you're putting heat into the system. So it's a positive.
Oh, yeah. But I'm confused about this one. So I don't know which one is positive, which one is negative.
So just if you look at the question, so heat is required to warm. You're putting heat into it. Heat isn't leaving. So if I said instead that the temperature goes from 90 to 10, that would be exothermic.
Okay.
Because the object is becoming colder.
Okay.
Yeah. Hopefully that cleared up anything. I will give you guys until 7:21 to do this problem. How about what did you guys get for your answers?
I get negative 483 degrees Celsius.
I got the same thing.
Okay.
I got 483 positive.
Okay, I got 483 as well. How about we go over how we got that answer?
Yeah.
Okay. So I can write.
We can start with 250. Yeah. Q is 215 kilojoule. So we can convert it in to joule. So it is 215,000 joule.
Yes. So 1 kilojoule, 1,000. So then you get 215.
Yeah.
Yes. Okay. So
and
now
then we use the formula that Q equal M. We have M. M is 1,000 grams.
Delta T.
Yeah. Okay. Yeah. And C we have a 0.385 joule. And then delta T. We just skip delta T. No need to.
Yeah.
Yeah.
So for this one, I just want to say is that I'm not going to go over the specifics of the unit conversions because you guys can do the conversions from kilograms to grams. If you guys are confused about anything, just let me know throughout, okay?
So delta T
from here,
equal Q over MC.
yes. So you rearrange the formula.
Yeah.
And then you get M times C.
Yes.
So if you do that,
we have delta T equal.
You can go like this. It goes, you can just go T initial minus T minus 75.
What is
75, I mean. 75 minus T initial. Okay. Yeah.
Yes.
Sorry. Equals to your Q, which is 5,000 joules over your M 1,000
by
times
0.3. Yeah.
So again, units crossing. Joules are getting out. So let's solve for minus T initial first. Let's solve the right side. You should get 21,500. You should get 558.
Yeah.
0.44. If you subtract 75.
Yes.
You should get your 483.
Yeah.
0.44, and you have a negative T initial. If you divide it by -1 for each side, I'm going to put my final answer here. Your T initial should be negative 483 degrees Celsius. You can check it. If you guys check your answer, what you just do is you plug in all the numbers to see if you get the correct Q. You also have to convert over to kilojoules. When you do, you do get the correct answer. Okay, so let's go on to calorimetry. So calorimetry is all those fun combustion problems and everything. So we can measure how heat evolves in a chemical reaction. So it's a thermal energy exchange between the reaction, which is the system and its surroundings. So an example would be when you drop a heated metal cube into a beaker of cold water or room temperature water to observe the change in temperature. So the change in temperature, delta T, is related to the heat that is absorbed by the entire calorimetry, which we'll label as Qcal. So Qcal we have right here can be equal to the specific heat of the calorimetry times the delta T. This is, remember, note this down. You will use this a lot for the following 3 examples. So the specific heat of the calorimetry is the heat capacity of the bomb calorimeter. So it's how hot it can get before it explodes. Think about it that way. Assume no heat escapes and the amount of heat gained is equal to the heat released by the reaction. This is us just giving you guys a given, something for you guys to assume. You guys won't change it. So the change in the heat absorbed by the entire calorimetry is equal to the negative heat release of the reaction. So we'll do the practice problem. We'll do the first one together again, and then the following 2 will be a little bit harder. Okay. So the first problem, let's list down what I said to remember earlier. So you want to know, I'll list it up here. You want to know that Q cal is equal to specific heat of calorimetry times delta T, as well as the heat of the calorimetry is equal to the negative Q of the reaction. Therefore, we can also write this as Q reaction equals to delta E of reaction. So that's the whole energy of the entire energy of the reaction. So from this, what we're going to do is we're going to read the question and we're going to derive an equation from it. So the combustion of toluene, you're going to use this mass, has a change in energy of the reaction of negative 3.91 times 10 to the 3 kilojoules per mole. When 1.55 grams of toluene undergoes a combustion in a bomb calorimeter, the temperature rises from, this is your T initial, to 37.57 degrees Celsius, which is your T final. Find the heat capacity of the bomb calorimeter. So we're finding C for this. Given this information here, we're going to come up with this where we're going to draw a relationship. So if we rearrange this, we can get C cal on one side, where Q cal over delta T. But we also know Q cal is equal to your negative Q of the reaction. If it's that, then we can also go to this part right here, where it's equal to the change in energy of the reaction. So we can rewrite this as like this right here. Delta E of the reaction, negative, over delta T. So let's plug this in, okay? So we have your heat of reaction, and we're gonna go in with delta E of your reaction equals to 1.55 grams of C7H8. So from there, we need to get the molar mass of toluene. I'm going to give it to you guys here, and it is 92.15 grams. So we're going to use that conversion to get into moles. Well, actually, really to just cancel out. Sorry, yeah, to get to the moles. In 1 mole. And then you will notice that we have the kilojoules per mole. So we can just plug that in to get the kilojoule, which is what we wanted. So it's 1 mole to negative 3.91 times 10 to the 3rd kilojoules. Your answer for this should be negative 65.77 kilojoules. Now that we know the delta, the change in reaction when it's applied to toluene per the amount used, we can plug it in. So let's plug it into the formula. So it's negative 65.77 kilojoules all over your change in temperature, 37.57 minus 23.12. Your specific heat should come out to be 4.55 kilojoules per degree Celsius.
I have a question.
Yeah.
So if it's asking for it in joules, would we convert it to kilojoules? Sorry, convert it to joules, but it's also asking for joules over grams times degrees Celsius. So where would you get the grams to include it in the units?
So where does it?
Because it said find the heat capacity of the thermometer and then joules per degree.
I think I forgot to change it. Okay, so if it's given to you in the degree, in the kilojoules right here, sorry, my bad. I'm going to change this. what we're going to do is we're just going to multiply across, where you're going to do 1 kilojoule to 1,000 joules.
Yeah.
And that should give you your dimensional analysis right there for the conversion. So let me plug that in. Negative 65.77, 37. And you just, again, so your answer will be in 3 sig figs. So it should be 4.55 times 10 to the third joules.
So, like, was it a typo in the question asking it for joules per grams degrees Celsius? Like, should it?
Yeah. I think I put the joules in afterwards, but originally I had just done it straight across to kilojoules. It just depends on what your professor's asking. If they ask you for joules and it was given in kilojoules, you're going to have to do conversions. If not, then you can leave as is if they just want your answer in kilojoules.
No, yeah, because the question was asking it for like joules over grams times Celsius, and then like I know the answer we get joules over degrees Celsius,
degrees Celsius.
Grams.
I think that was an error on my part earlier. I was editing it.
Okay.
Sorry, so ignore this.
Okay.
It's just joules per degree Celsius. My bad.
Okay.
I was inputting units earlier. I was like, I'm missing units. Okay.
Sorry.
Any other questions? Yeah?
Yeah, I have questions.
Mm-hmm.
We have the formula Q calorimetry equal C means specific heat capacity of calorimetry by delta T. And then we have a Q calorimetry equal negative Q reaction. And then we have Q, so Q reaction equal Q delta E reaction.
Yes.
We don't have the formula of delta E reaction, right? We just we just go back.
Yeah.
Is that correct?
That's basically what we did. So we just have these rules. So if I'm saying that Q reaction is equal to the delta E reaction, then you can interchange them and replace them for each other to give you that one whole formula to use.
So if we face such a kind of question, what do you recommend us to start? Step by step.
So in this case, I would actually say to write down what you have first and what they're asking for you. Once you get that, see if any of these rules apply. If they do, then use them. In this case, I would recommend, because many problems when I was in Gen Chem and even helping students with Chem 2A and Intro to Chem, they might use these reactions and these rules. It's helpful to know them. They're really useful for your exams. So having these in mind when you're applying to calorimetry problems would be great. Sometimes they'll change delta E reaction and refer to it as delta H reaction. So they're interchangeable in some ways when you're doing the same calculation. Does that answer your question, Trung?
Yeah, I think so.
Yeah? Okay. So are we okay? Yeah?
Oh, sorry. So it's just making sure, like, the equation Q of the calorimeter equals the C times delta T. That's just for calorimetry, right? Or
yeah, it's for calorimetry.
And is this it's specifically to a bomb calorimeter?
This is to other calorimetry problems as well.
Okay.
This can be applied to, yeah. That's why I said, like, keep it in mind. We're going to use it for the other examples as well.
Thank you.
Okay, so let's do the next one. I'll give you guys 5 minutes again, and then we'll just walk through it. There's one more problem after this, okay? Okay, so let's look at this. So I'm just going to pull this again from the top. We want to have this. Okay. So if we're looking at this question, it's asking us for the delta E reaction in kilojoules per mole of hexane. So delta E reaction can be written. How did you guys, what formula did you guys
C
derive from it?
calorimetry. Yes. Calorimetry. Delta T. Yes.
Okay. So for this, it's right. So if you plug it in, you can't do so yet because you don't have the correct units for your calorimetry specific heat because it's too, wait, no, you have it, but you don't have the information to do the molar heat. So we'll do the delta heat, the delta E first. So you know that specific heat is the 5.73. So it is 0.73 kilojoules per degree Celsius. And you're going to multiply to change in temperature. 38.13 minus 25.87. And then from there, you actually wait, I think I caught something. So delta E reaction is to Q reaction. Okay, let's leave it as that for now. So delta E reaction should be equal to 70.2498. Did you guys get that?
Yes.
Sorry,
Kilojoules.
I have a question.
Yeah.
So you mean C calorimetry is 5.73 kilojoule over.
Degrees Celsius.
This is a C calorimetry.
Yes.
C calorimetry. Can you explain what it is?
So it's like the specific heat of a regular metal you would get, except you're just getting different units because there isn't a mole to it. You're going to apply it.
So usually it is given, or
It can be given, or you can calculate it like we did up here.
okay. So, but
Yeah.
this one is given.
Yes, this one is given. It just depends on which one your professor wants you to find. So you're given this, you're not done yet. So now what you have to do is you're going to use your 1.55 grams of hexane, and you have to convert it to moles. So you have 1.55 grams of hexane, C6H14. Just multiply across. It's 86.2 grams to 1 mole. You should get 0.01798 moles. H14. So from there, you're going to use this information. I'm going to bring it over here. We'll plug it in. And what you're going to do is you have to divide your change in reaction by your mole. of C6H14. Because what you are finding is kilojoules per mole, right? So if you do that, you get 70.2498 kilojoules over 0.01798 moles. Your answer was 3.91 times 10 to the third kilojoules per mole. And if you're looking at it, if it's a combustion reaction, is heat being absorbed or released?
Release.
Release.
So it should be a negative
Yeah.
3.91. So
Okay,
that's
I
your
have a
answer.
question.
Yeah.
So when we were doing the stoichiometry of the grams to the mole,
Yes.
I just continued to plug in like 1 mole. No, so whatever like kilojoules we got.
Yeah.
And that over.
Yeah, you can do that too.
Okay.
Yeah. I was just doing them in parts so that you guys can see it.
Yeah.
Yeah.
But I didn't end up with the answer. I don't know.
So if you plugged it in from here, let's say, okay, let me write it. I'm going to minimize this for, okay. Okay, there you go. Okay, so if you go 1.55 grams times 86.2 grams, 1 mole C6H14, you don't want to cancel out your moles. So what you're just going to do is, well, actually you have to bring it down. It's more difficult to do it like this. It's going to put it that way.
Yeah, I think it made sense when you said
Yeah.
don't cancel out your moles because you need that.
Yeah, that's why. So I would say try not to do it this way just because you want your moles to be your bottom unit.
Right.
You can't divide it if it's on top. So I would say just bring it out like we did here, where you just plug it in, where you'll have your desired units where you want it to be. It's more easier to do stoichiometry when it's a straight across, but in this situation, it's more difficult to do so, okay?
Okay, thank you.
How about you guys take a screenshot of this? I'm gonna move. So challenge problems, I put it up here. I strongly recommend try it yourself, work it out, and schedule a tutoring session to check your answers. The chemistry tutors will be provided with the key. Okay. Again, this is extra. It's up to you if you'd want to do it, but I strongly encourage it because it is preparation for your exam if you guys are practicing. This one's a little easier. So this is the first challenge problem. We made 4 of them for you guys. This is challenge problem 2. This is the third one. So this is challenge problem 4. This is several applications, so it's very interesting. So let's go to that heat. So my bad, I did not do it completely as well. So when you're reading this, big factor right here, it says the copper gave off 215 kilojoules. What that means is that your Q is a negative because it is exothermic. So if Q is negative and you plug it in, exactly how we did earlier, just changing that sign, you should get your final answer to be 633 degrees Celsius.